This is the homework, continuing the homework on implicit differentiation, and this is page 171, problem number 8. I have actually typed these answers up already, so I'm just going to kind of narrate through this. So in number 8, we are finding the derivative by implicit differentiation, and we're taking the derivative with respect to x. So the first term, I notice I have e to a power, and the derivative of e to a power is e to the power times the derivative of the power. I have the second term is x squared, so that's in terms of x, so that's going to be easy. And the third term is in terms of y, and then a constant on the right-hand side. All right, so let's begin with the first term. So the derivative of e to a power, I'll just remind you and write that over here on the side. So e to, don't do it in blue, e raised to a power, the derivative will be e raised to that power times the derivative of the power. So when I look at my work over here, here's my e to the power, and then the derivative of the power is a product, so we need the product rule. So I have the first times the derivative of the second, plus the second, which is y, times the derivative of the first. So all of that part right there is the derivative of e to the power. The derivative of x squared with respect to x is 2x, so that's easy. And the derivative of y squared is going to be, by the chain rule, 2y, there's the chain dy dx. The derivative of 10, of course, is 0, and that's there. Okay? Now, we have to get the dy dx term by itself, so what I'm noticing right here in this first term, I'll circle it for you. This first term has a multiplication going on. There is a dy dx that is locked, so to speak, on the inside of those parentheses, and I can't start manipulating that dy dx until I get it out of there. So the key to success here is distributing the e to the xy term in order to unlock, so to speak, the parentheses to get that dy dx out of there. So when I erase this stuff and get it out of the way, I'll show you what's happening here. So I am distributing the e to the xy to the first term and the e to the xy to the second term, and this is what I get when I distribute. The 2x stays, the 2y stays, the dy dx stays. So that was all distributing. All right, now I have my dy dx terms. I have a dy dx term right here and a dy dx term right here. So I'm going to keep the non-dy dx terms on the left-hand side and add or subtract the dy dx terms to the right-hand, or I did it reverse of that. So I kept the dy dx terms on the left side, and I added / subtracted the non. So the 2x, there you go. So the 2x got subtracted to the left-hand side, and the y e to the xy got subtracted to the left-hand side. I factored out the dy dx from the two terms that I had, and now, of course, to get dy dx from both on one side, I'm going to divide by e to the xy, x e to the xy minus 2y. So again, really the big deal here is, in order to get dy dx by itself, you have to distribute in order to, quote, unlock the dy dx and get rid of those parentheses. All right, problem number 20. In number 20, we have in the first term an ln, so I can see right away that, get a pen, go orange. The first term, ln of xy, the derivative of ln is u prime over u, so I'm getting my math eyes ready, thinking about what I'm going to need to do here. The second term is in terms of x, that's going to be easy. The third term is a constant, that's going to be easy. So I don't know why this 51 is right here. Let me get that. Okay, so I got that 51 out of the way. Let's go back to number 20. All right, so u prime over u for the first term. So because we have a product here, when we do our u prime, pen. All right, so u in this case is x, y. So u prime is going to need a product, so that'll be first derivative second plus second derivative first. So that's where that's coming from. So that is the u prime, and then we're going to divide that by u, which is xy. the derivative of 5x is just going to be 5, and the derivative of 30 is going to be 0. All right, the dy dx term that I am trying to isolate is right here. So the first thing I'm going to do is I'm going to subtract 5 from both sides, and then I will multiply both sides by xy. So I subtracted 5 from both sides. Now I have a complex fraction on the left, so the next thing I'm going to do is to multiply, get a pen, the next thing I'm going to do is multiply both sides by xy. And when I do, I will get negative 5xy on the right-hand side. Then I'm going to subtract y from both sides, because remember I'm trying to isolate dy dx. And then I'm going to divide both sides by x to get dy dx by itself. So that's the implicit differentiation, getting dy dx by itself. And then we're moving into look at the directions. We're trying to find the second derivative. Notice how that's written, d squared y over dx squared. So let me take just a second to explain that notation to you, why the square is here on the d and then the square is here on the x. So think about when you have a function whose name is y and we take the derivative of y, one way of writing that is dy over dx. So what we just did there, the operator is to take the derivative with respect to x of y. So if you do that, you can see that that would become dy dx. All right, so that's why we get that as our result. Now, if we take the derivative again, which is the second derivative, I'm going to take the derivative of a function with respect to x, and the function that I'm taking the derivative of is the first derivative, dy dx. So this is my operator, just like back here, this was my operator, and then you can see I get d squared y, and then the dx squared is not really meaning the x is squared, it means the whole dx, the whole term, is squared. So that's what's happening with that, and why the notation looks like that. All right, so moving on to number 51. So we're going to have to take the first derivative to get to the second derivative. So let's start over here on the left. The derivative of x is, 51. The derivative of x squared is 2x. The derivative of y squared is 2y dy dx. There is your chain rule. And the derivative of 36, which is the constant, is 0. I'm going to subtract the 2x to the right-hand side over here, and I'm going to divide by 2y, and that is my first derivative. Second derivative is going to require taking using the quotient rule. So I'm going to have down, and there it is right there, d up. This is the down d up right here, because the down is y, and the derivative of negative x is negative 1. Then I have minus, be careful with your signs. There's my up, and the d down, I'm going to use the chain rule. So the derivative of y is dy dx over down, that's my y squared. Now the key to success on the second derivative is really substituting in the dy dx that you got. So back over here, we already got dy dx right here, negative x over y, and that gets substituted in place of, because they're equal, they're equivalent, in place of dy dx. That goes there. Now the rest of this is an exercise in algebra, so I'm going to keep the well, let's see, maybe I'll come over here. So how did I get to this step right here? So I had negative y plus, I'm going to multiply the x times the negative x, and that gives me negative x over y. So that's just what happens so far with that first term. I distributed the negative x. All right, so then I'm going to get a common denominator, so because this is over 1. The common denominator is y. So I'm going to multiply the first term by y, so that makes negative y squared, and, whoops, I didn't square that when I wrote that down. So when I multiply x times x, I get x squared minus x squared. So that's where that came from. It was literally getting a common denominator after distributing. The y squared in the denominator stays there, so then we have all of this over y squared over 1. And so we know when we divide fractions, we multiply by the reciprocal, so that becomes multiply by 1 over y squared. So that's gone. And y times y squared gives me the y cubed right here. Now, this is not really something I would take points off for, but it's something that pops up periodically. Maybe if it were on a multiple choice test, you'd have to figure it out. So negative y squared minus x squared, if I factor out the negative, is the same thing as y squared plus x squared. And if we go back to the original problem, x squared plus y squared is equal to 36. So I can substitute that in place, and that's where the negative 36 comes from. But if you got it to here, right there, I'd be totally happy, totally fine if you did not notice the factoring and substitution. So take a minute to go back and look at that fraction work that I did, and reproduce that for yourself. Don't just watch what I do. All right, so let's clear the screen. Let's clear these annotations, and let's go to number, what's next? 54. In number 54, let's make a plan of attack. So the first term is a 1, and that's easy to take the derivative of. Be careful right here. I see the product. Derivative of x is going to be easy. Derivative of y, dy dx. So, and that'll get us to the first derivative. I have these out of order. That's okay. Let's move this down and go down to number 54. All right, so in number 54, let's find the first derivative. So, let's see. I lost the problem, though, when I moved it down. Let's see, 54. Let me write that down here. So that's going to be 1 minus xy equal to x minus y. All right, so the derivative of, coming back down here, the derivative of 1 right here is 0. And then the derivative of, remember I said I have a product right here, so I'm keeping my negative on the outside, and then right here I'm doing the product rule for x times y. So first derivative second plus second derivative first. On the right-hand side, the derivative of x is going to be 1, and the derivative of negative y is going to be dy dx, or negative dy dx. Here we go again. I'm going to distribute and distribute, so that's going to give me the negative x dy dx minus y, isolating the dy dx terms on the left-hand side, the non-dy dx terms on the right-hand side, factoring out the dy. So right here, when I factor out the dy dx, that will leave me with negative x plus 1 from here, and then dividing to get the first derivative. Right now with my math eyes, I notice that I'm going to need to do the quotient rule. So here we go. Here we go. Looks ugly, but it's not that bad. So I have down, and then the d up. The derivative of y is dy dx, and the derivative of 1 is 0. Minus up, which is y plus 1, over d down. The derivative of negative x is negative 1, and the derivative of 1 is 0, over down, down. All right, then I'm going to substitute. Let's clean a little bit here. Then I'm going to substitute my dy dx in place of dy dx, which is what's happening right here. And this kind of turns out to be a beautiful thing because the negative x plus 1 divides out with the negative x plus 1. And that leaves me with y plus y, which is 2y, and 1 plus 1, which is 2. And that was a pretty nice clean. I didn't have to do a whole lot of complex fraction work there. And then let's clear the annotations and go to number, whoa, edit, undo. What did I just do there? Clear the annotations. I must have cleared the objects. Let's go to number 55. And let's make a plan of attack up here in number 55. So in number 55, the derivative of y squared, that's going to be easy, 2y dy dx. The derivative of x cubed is 3x squared. That'll get me quickly to the first derivative. So there it is. The derivative of y squared is 2y dy dx. The derivative of 3x squared, x cubed is 3x squared. That was easy. Isolating dy dx is easy. And I've created a quotient, so I'll need the quotient rule. So let's see what happens. So I have down d2y dx, 6x, minus up d down 2, there's my chain, dy dx, don't forget about the chain, over down down. So 2y squared is equal to 4y squared. So that's where that came from. I got to substitute my first derivative, which is right here, in place of dy dx. So that's what's happening right there. So 2 times 6 is 12, and x times y. So that cleans up the first term. I multiplied 3 times 2, and that's where the 6 comes from, x squared. The next thing that I notice is that 2 divides into 6 3 times. Actually, that's not how I cleaned it, but I could have, so let's erase that. Let's just follow my work here. So I multiplied 6 times 3 to get 18, and x squared times x squared to get x to the 4th. Now, where did this 24xy squared come from? Well, I have a 12xy over 1 minus 18x to the 4th over 2y. So I need to get a common denominator. So the common denominator will be 2y. So I'm going to multiply over here the denominator by 2y and the numerator by 2y, and that's where I'm getting the 24xy squared. Okay, it's not magic, it's just math. All right, so come back over here. That's where the 24xy squared came from. So now I have one fraction in the numerator and one fraction in the denominator. And in the denominator, I can take that 4y squared and put that over 1. So I can multiply by the reciprocal and make that 1 coming over here to the right-hand side. I can dividing by a fraction is multiplying by the reciprocal, so that's 1 over 4y squared. Multiplying those together will give me, that's where the 8y cubed comes from, which is right here. Now, the crazy part that's happening next is not really a have to, but when I go back up to the original problem, I know that everywhere that I see a y squared, I could substitute an x cubed. The reason I'm showing you this is because the solution manual actually does this. So in this y squared, I can substitute an x cubed, and the y cubed is the same thing as y squared times y. Again, you don't have to do this. And the y squared, again, is the x cubed. I could keep, there's so much that I could keep cleaning and cleaning and cleaning by doing the substitutions, but you really don't have to do all of that. If you can get it to right here, I will be perfectly happy, even though there's other cleaning that could occur. So that's your homework on for this set.